Okay, everyone. So in the last class, we were looking at implementing a stack of integer values using a linked sequence of nodes. So in the last lecture, we got introduced to this to the typedef statement. So a typedef statement lets you create an alias for an existing type. It's commonly, well, is it commonly? You'll often see it used when you're working with structures. So here we have a structure called ql_stack_tag. You'll see it used to replace the full structure name with a shorter structure name. So here we've got a typedef that says the name or the tag ql_stack means exactly the same thing as writing struct ql_stack_tag. So in this particular example, it saves the programmer a little bit of typing. You don't have to write struct everywhere. But other than that, it doesn't really serve any other purpose. So we actually managed to get through about half the implementation of the stack. So let's jump into the source code. So remember, if we're going to use a linked sequence of nodes, we have to define a structure for our node. So there's our definition for our node. Right, and so every node holds an integer element, and it simply holds a pointer to the next node in the sequence. Right. Notice here I haven't used a typedef for node. You could if you wanted to, but I haven't done so. So instead of writing node everywhere, now I'm stuck writing struct node everywhere. But if you wanted to, you could create a typedef and alias struct node to something shorter, like node. I then need a structure for the stack itself, right? So this would be like creating a stack class in Java. You're going to keep track of the top node of the stack. So there's our pointer to the top node of the stack. And you're going to keep track of how many elements are in the stack, which is our size. For a new stack, you simply allocate memory for a new structure to hold the stack. So you're going to allocate memory to hold one of these, which you can do by using malloc and passing in the size of a QL stack. Remember, QL stack is typedef to QL. Sorry, remember that struct QL stack _tag is typedef to QL stack. So new makes an empty stack, so there is no top node. So we make stop equal to null, and there's no elements in the stack, so we make size equal to 0. And then we return a pointer to our stack structure. Is empty is straightforward. You just look at size, right? Stack is easy. You just return the size. Right? Pushing an element onto the stack is exactly like pushing an element onto the stack in Java. What do you have to do? You have to make a new node. So there's our new node. Right? Or there's our pointer to our new node. Once you've got a pointer to your new node, you just fill in the fields of the node. You fill in the members of the node. Right? So the element in the node is just equal to the element that was pushed onto the stack. Right. You now hook up your new node so that it points at the current top of the stack, and then you adjust the top of the stack so it points at the new node. And of course, don't forget to increase the size of the stack by 1. Right. And again, popping a stack is just like popping a stack in Java, except we're going to return the popped element by pointer. So the caller is going to pass in a pointer to an int variable. Right. Our function is going to write into that variable. So if our function needs to write into the variable, we need a pointer to the variable, which is why this is a pointer to int. So when you pop the element of the stack, you're going to remember what's the old top of the stack, right? Because I'm going to remove this in just a second. The element sitting at the current top of the stack is just the element sitting in old top. I'm now going to remove the node, old top, by adjusting stop. Right? So stop equals old top next. Right? Decrease the size of the stack by 1. And then I'm going to free the old top node. Right? And why do I have to free the old top node here? Because we popped the element off the stack. We no longer need the node that is holding the element. So don't forget to free the old node right there. You have to free the node because it was allocated in push, right? So remember, in push is where we actually dynamically allocated a node. We never freed the node in push because it doesn't make sense to free it there, right? When does it make sense to free it? Well, it makes sense when you pop the element off the stack, right? So here is the call to free, right? Free up the memory that's associated with the node. Don't forget to write the element that was popped off the stack into the user's variable, right? Which they passed in by pointer. So dereference the variable, or dereference the pointer, sorry. Right. That gives you their variable that they passed into the function, right? And now I can store the element into their variable. So remember this because in the next part of this lecture, that's going to change to something else. Right now, remember why we're doing it this way, because we want to use the return value to indicate whether or not there was an error when we tried to pop the stack. Right. So for example, if S was null when they called the function, there's no stack to pop, right? So that should be an error of some kind. So we're using the return value as an indicator that an error has occurred. There's a bug in this function that I realized before the lecture. So you can't pop an empty stack either. So you really should check whether or not the stack is empty here, right? So if someone passes in a null pointer for the stack, or if the stack that they passed in is actually empty. Right now, you could do this in a bunch of ways. So there is a QL stack is empty. Right, that's probably the cleanest way to do it. Right, so if the stack is empty, or if someone passed in a null pointer, we can return null because there's nothing to pop off that stack. So that would be a better implementation of pop. Right, if you don't check if the stack is empty, that will cause something bad to happen, right? Because old top will be null at this point, and then you try to access an element via a null pointer, and you'll probably end up with some sort of error when you run the program at that line there. All right, what about printing a stack? So printing a stack is relatively straightforward. You just have to iterate over the nodes of the stack. This print function is a little bit fancy. It lets you print out a string before the stack, and then it lets you print out a string after the stack if you want to. Right, so pre or post is null, then nothing gets printed out before or after. Otherwise, whatever the string is that gets passed in for pre or post gets printed before the elements of the stack. Right. And so here, if there is a string passed in as pre, it prints the string. Right, then it prints top. Right, and now if the stack is not empty, we iterate over the nodes of the stack. Right, so whenever you're printing out a sequence that's not empty, you always start by printing out the first element. So the first element is given by the node that's equal to the top of the stack. Right? So n is equal to s top. I'm going to grab the element out of n and print that. Now I can print it because I know that this is a stack of int. Right? In the next part of this lecture, we're going to change this so that you have a generic stack. And this becomes a little bit more complicated to deal with. Right, because I know it's an int, I can just print it as an int, right? And then advance n to the next node, right? So we printed out the first element of the stack, right? And now to print out the remaining elements of the stack, right? You check, are there remaining elements of the stack? And if there are, this is where you put your separator in, right? So if you want to print out your elements as a sequence, so something, comma, space, something, comma, space, something, comma, space, something, right? It's inside the loop where you first print the separator. So here are the comma space, right, followed by the element, right, and then advance n to the next node in the sequence. Right. Eventually, n reaches the end of the sequence, and it's equal to null. Your loop stops, right, and you printed out all the elements of your sequence. So now finish off printing out the sequence, right? So now I'm going to put the string bottom at the end to indicate that we've reached the bottom of the stack. And if there's any postscript, sorry, we'll print that out as well. I'll show you an example of what this looks like in just a second. Well, let's do it now. So there's a little demo program that you can run in the directory containing the QL stack code. It's just called demo.c. Right? If you run that program lets you type in some numbers on the command line, and it just pushes 1, 2, 3, 4, 5 onto stack 1. Why did I call it Q? Anyway, it's called, I don't know why it's called Q. And then it pushes -1, -2, -3, -4, -5 onto stack number 2, or Q2 in this case. Right, and so when you see when you print it out, the elements of the stack, it prints out top colon and then the top element followed by the bottom. Right. So that's the format that you get when you use that particular print function. Right. And notice that all the elements are separated nicely with a comma and a space. There's no dangling comma and a space at the end, right? Which happens if you implement print by printing out each element and the separator inside the loop. Right. You can pop the stack, and you can see every time you pop the stack, it gets smaller each time. Right, and the returned element shows up there. Okay, there's one more thing we got to do, and that is we have to free the stack. So if someone has a stack, whether or not there's elements in it, you still have to free the pointer. You have to free the memory that's allocated to the stack structure itself, right? So the thing that stores the pointer to the top node and the size of the stack. So we have a function called QLStackFree, takes in a pointer to a stack. Right? If the pointer is null, there's nothing to do. Apparently the stack's already been freed, or there was never a stack to begin with, so you simply return. Right. Now, when you implement this function, you have to realize that you have to remember that the nodes, where did they come from? They came from being dynamically allocated. Right. So you have to remember to free each node as when you free the stack. Right. It's not sufficient simply to free the stack itself. Right. All of the memory that's used up by the nodes also needs to be freed. One way to implement the function is to simply write a loop and pop all the elements off the stack. Right. Every time you pop, right, you free the node. So that would work just fine. Right. It's slightly more efficient, like very slightly more efficient, to write the loop yourself. Right. So starting at the top node, right, as long as there's a node, so while n, right, I'm going to remember what is the next node in the sequence. I need to remember this because what I'm going to do next is free the node n. Right. If I free the node n, I don't have access to next anymore. So before I free the node, I have to remember what is the next node in the sequence. Right. Once I've remembered that, I can actually free the node n. So that releases the memory allocated to the node. And then you can advance n to the next node in the sequence. Right. Notice here it's n equals next. It's not n equals n next. Right. If you try to write n next here, well, you freed n. So that's going to blow up in your face. Right. So it's n equals next here. Once you've freed all the nodes, well, now you can finally free the pointer to the stack itself. Right. So now you can free s at the end. And there is a completely functional linked stack implementation in C. Right. It really does match. It really does map to Java code. Right. As long as you remember that you have to allocate the stack structure itself. Right. Rather than relying on Java's new to create the stack object for you. Right. And of course, you have to remember that you have to clean up after yourself in C. So you have to write a function that frees the nodes, that frees the stack and its nodes. And you have to remember that when you pop an element off the stack, you really ought to free each node that gets popped. All right. Any questions about implementing a linked stack? Okay, so the next lecture the next notebook, I should say, talks about implementing a stack again, but this time it's a stack of any element type, right? So the problem with our previous stack class is that the problem with our previous stack implementation is that it's a stack of int. If you want a stack of double or a stack of strings or a stack of char or a stack of anything else, right? Your only recourse is to make an entirely new header file. You have to make an entirely new source code file. You have to change its name because you can't have the same name as a type. You can't have two types with the same name in the same program, right? And there's a whole bunch of code duplication that happens, which you want to avoid, right? And so what we'd really like to do is you'd like to make a generic stack. So I'm going to show you one way to do that in C. It differs from how you do it in Java, right? So in Java, you've got the stack class that is already generic, right? So if you want to make a stack of integer, you just say you want a stack of integer, and away you go, right? If you want a stack of double, you just make a stack of double and off you go, right? You can make a stack of any type that you want, right? And it just works. You don't have to do any extra work on your part as a programmer. Whoever created the stack class doesn't have to do any extra work either, right? So there's no one class that corresponds to stack integer, right? There's no one class that corresponds to stack double. There's just one stack class, which is kind of nice. Right? So in languages that support generic types, right, the programmer only implements the type themselves once. Right? Depending on the actual language, exactly what gets created when you make an instance of the generic type depends on the language. So in Java, as it turns out, you end up with something that's just called stack. Right? The element type is actually thrown away after it's compiled. So at runtime, the virtual machine doesn't actually know what element type is in there, which is funny. In C++, the compiler synthesizes a new type for every generic type that you make. So if you made a stack of integer, the compiler makes a separate class corresponding to a stack of integer. If you then make a stack of double, it then makes a separate class corresponding to a stack of double, and so on and so on and so forth. Right? So the different programming languages have different mechanisms for how all of this is actually implemented. C has no generics, so we kind of have to work around the problem ourselves. So how does this work? All right, so that's what our node looks like for our stack of int. Right? This could be a queue, it could be a list, right? It doesn't have to be a stack. So if we have some collection of int, right, our node can hold the int itself as an element. Right? If you want a generic type, so a type where the element type can vary, the most straightforward solution in C is to pick a type that can represent any other type. There's only one in C. Right? So in C, you've got a pointer to void, right, which can point at anything. So it looks like that's going to be our solution, right? So a pointer to void is a pointer to a value of an unspecified type, right? So a void pointer variable is allowed to store a pointer to anything, right? It doesn't matter if it's an int or a string or a double, right? It can store that pointer. So we're going to take this approach for our node. So our node for a generic, a generic node, I guess, is going to store the element by pointer, right? It's a void pointer, so our implementation, our stack type, does not actually know what it's a stack of, right? So it has no knowledge of the element type, which is going to complicate things, as you'll see. Okay, so there's a bug in this notebook right there. When I copied over the node type into the notebook, I didn't change the element type. All right, so QLG stack is our linked generic stack implementation. So our node is going to hold elements by pointer, right? And the element, the pointer type will be a void pointer. Everything else stays the same. Oh, that should be QLG stack as well. So when I copied stuff over, I really didn't edit it properly. QLG stack. There we go. So the stack type itself doesn't change at all. There's still a pointer to the top node, right? And we still keep track of the size. So what does change? Init doesn't change, right? If I want to make a new stack, it doesn't matter what the element type is, right? I'm going to allocate a new node for the, I'm going to allocate a new one of these things here, right? And that's it. So that doesn't change. The init doesn't change. When I push an element onto the stack, though, that's going to change a little bit. So instead of pushing an int onto the stack, I now need a pointer to an element, right? And it's going to be a void pointer to an element. When I pop an element off the stack, this gets a little bit more complicated, right? So remember when I popped an int off the stack, we required the user to pass in a pointer to an int, right? The function writes into the object pointed at by the pointer. If our elements are pointers to void, then when I pop an element off the stack, right, that's going to give us a pointer to avoid. It's going to give us a void pointer. If I want to store that in the caller's object, they need to pass a pointer to a pointer in this case, right? So again, the double star shows up, right? So our popped element, we're going to write the value of a pointer into the caller's variable, which is also a pointer, right? So they need to give me the address of that pointer, which is why the double star shows up here. Okay, so let's go into the source code and see what actually happens here. So QL, which I did not open, sorry. So in the source code directory, there's a QLG stack directory. Okay, so in our source code, so here's new. If you compare new for this stack compared to the other stack, it's exactly the same code. Right? Allocate a memory for one of our stacks. Right? Set top to null, set size to 0. Right? Is empty is exactly the same. Right? Look at s size. Right? The function that returns the size, just look at s size and away you go. Okay, so what changes in push? So our element type changed. It's no longer int, right? It's now a pointer to something, right? Where we don't know what the something is, right? So keep that in mind, right? When we're writing our stack code, we don't know what the something is, right? Code here is exactly the same as the previous example, right? There's nothing different. Pop, exactly the same. There's nothing different, right? Even the line where we dereference the pointer and write the element is exactly the same. Right. Now when we dereference our pointer, right? So if I dereference popped, right, that gives me a pointer to void. Right? What is our element type? Well, it's pointer to void. So that works just fine. Right? Code's exactly the same. Oops, sorry. Okay, so where do we run into a problem? Let me just quickly jump to the notebook because I want to make sure we're at the right place. Here we go. Okay, so where do we run into a problem? So let's go back and look at our previous stack implementation. So where's print? Here's print. Right. So when we printed out our previous stack, we knew that the elements were of type int. So there, we know what to write. Right? To print out an int, use printf and %d. Right. Now, in our generic stack, we have a problem. Right? Oops, sorry. So there is where we printed out the element before, right? We printed out an int. Here we've got a problem. Our function doesn't know what the element type is, right? So there's no way for it to print out there's no way for our function to print out the value, right? So there's no code that I can write here that'll magically print out the value in C, right? It doesn't work. So what do we require instead, right? So what we require instead from the caller or the user of the class of the type is that they tell the function how to print out their elements, right? And so that's what this thing here is, right? And so how do you print out anything in C? You call some kind of function, right? Probably going to call printf eventually, right? The problem is we don't know what to pass to printf. Who knows what to pass to printf? The caller knows what to pass to printf, right? And so what we want from the caller is a function that can print out their element type, right? The way you specify that in C is that you pass a pointer to a function. So this is all brand new. We haven't seen this yet in C. Right. Okay, so how do you do that? How do you make a pointer to a function, right? So remember what a pointer to a regular type looks like, right? Here's an int x, right? If I want a pointer to x, I write int star, right? And then I make my variable name, so p is a pointer, right? And I can take the address of X. All right, so how do you make a pointer to a function? Right. So to declare a pointer to a function, you take your function declaration and you replace the function name with brackets, pointer, your pointer variable name. Right? So you take the declaration of the function. Remember what the declaration of the function is, right? That is the declaration of your function. Right? So this function says it returns void, its name is print my user defined type, and it takes in an argument of type const void pointer. Right? So if I want to make a pointer to this function, I replace all of this with that. Right? So take that, substitute it into there, and that's your pointer declaration. So my pointer declaration becomes void, right? So the return type, the parameter list, right? And then round brackets star, the name of your pointer, right? So I've got pointer to func. Right? So the name of my pointer is pointer to func, right? What does the pointer point at? It points at a function that returns void and has one parameter of type const void star, or pointer to const void. Everybody got that? Right? There's your declaration. Right? I want to make a pointer to this function, so I need a variable. So to make the variable, I take all of this, delete the name of the function, excuse me, and replace it with round brackets star the name of your variable. Right? So believe it or not, that is the declaration of a pointer to a function in C. Right? It doesn't matter what the function looks like, you always do it the exact same way. Right? Copy the function declaration, replace the name of the function with round brackets star your pointer name. Okay, so once you've got a pointer to a function, what can you do with it? Well, you can store the address of any function that returns void and takes in one of these as your arguments. Right? So it doesn't have to be a pointer to that function. Right? Any function that has the same return type and the same parameter list, right? I can make pointer to func point at that function. Right? And so this is the mechanism that you have in C to tell some other function what to do at some step in that process. Right? Here's a function that can do the missing part that you don't know how to do. Right? So for our print function, we're going to pass in a function that knows how to print one of our elements. Right? So if you want to, you can write the address of the address followed by the name of the function. Right? That's funny. Another bug. Okay. Where'd it go? Here we go. Okay, so once I've declared my variable up here, right, I can now use the name pointer to func as a variable, right? So it's a pointer to a function, right? And I can store the address of any function that has the appropriate return type and appropriate parameter list. Right? Now, because this is a pointer to a function, you don't have to take the address of the function, right? So if you want to, you can just write the function name and that's just fine. Right? So you don't actually have to take the address of the function. You can just write the name of the function. Everything works fine. So our pointer can point at any function that returns void and has const void star as its parameter. So if you had this function here, right? That thing returns void, has const void star as its parameter. So I can assign the address of print int to that pointer as well. Right? So I can actually I can change which function the pointer points at. Okay, once you've got a pointer to a function and it's actually pointing at a function, what can you do with the pointer? Well, you can dereference it, right? What does that do? It gives you the function. Right? So here I've made pointer to func point at the print int function. So if I dereference that pointer, that's just like calling the function, right? How do you call a function? Well, you write round brackets and then you pass in some values. Right. So to call print int, I need to pass in the address of something. Right. I need to pass in a pointer to something. Right. Void star means anything, right? So I can pass in a pointer to anything. So here I can pass in a pointer to A, in this case, right? The address of A. So again, because this is a pointer to a function, you don't have to dereference it in C. You can just write the name of the pointer. So, right, you can write the name of the pointer, and that is the same as calling the function. Right. So pointer to func, pass in your arguments, and away you go. Right. The compiler will automatically dereference the pointer for you and then call the function for you. So this is kind of cool. So all right, so let's see how this works. So I've got a program here that uses a pointer to a function, and that pointer is going to be able to print. Sorry, we're going to pass in a pointer to a function, and we're going to print an int, a double, and a string using the exact same pointer each time. Right. So here's print int. Right. It takes in a pointer. Now here it's print int, so we're going to assume inside the function that elem is pointing at an int. Right. So first thing you do, make a pointer to int and assign elem to it. Right. I'm breaking this all down into steps. You can do this all in one line if you want to. Right. But I need to convince the compiler here, right, that elem is actually pointing at an int. Right. At the moment, as far as the compiler is concerned, elem is pointing at something, but it doesn't know what. Right. So by making a pointer to int variable here and assigning elem to it, you're telling the compiler, hey, elem's actually pointing at an int. Right. Now that the compiler is convinced it's actually pointing at an int, you can dereference p. Right. And the compiler will look at whatever elem is pointing at and interpret those bits as though it were an int. I can store that in value, and now I can print the value. Right? Print double is the exact same thing. Right? It's called print double, so I'm going to assume that elem is pointing at a double. Right? Step one, tell the compiler elem is pointing at a double. Step two, dereference the new pointer. Right? That gives me the double value being pointed at. Step three, point the double value. Right? Notice the only thing that's changing each time is, the types are changing and the way that printf is being called changes. Right? For a string, strings are funny. So you're not going to dereference the. Now remember, if you have a pointer, if elem is a pointer to something, for a string, it's a pointer to the first character in the string. Right? So you're not going to dereference the pointer in this case. Right? You're simply going to make a new pointer. Right? Pointer to car. So that's pointing at the first character of the string. And now you can pass that pointer to printf. Right? Printf prints all the characters of your string. Right? But there's no dereference here, right? If you dereference it, you get a car, and then you have to print out a single car, which is not what you want. If you wanted to print out a structure, it's the exact same thing, right? So suppose you had a pointer to, suppose you wanted to print out a point to structure, right? It would be void print point to. Right. Step one, I'm going to assume that elem is pointing at a struct point two. Start being equals. All right, so p points at a struct point two object. Dereference so you can either dereference this now or use the arrow notation. I guess to be consistent, I'm going to use the arrow notation. Okay, so how do you print out the coordinates of a two-dimensional point? It's up to you how you're going to print it out. I'm going to use round brackets. Oops, sorry. I'm going to use round brackets, followed by the x coordinate, followed by a comma and a space, followed by the y coordinate. P dereference get x, right? P dereference get y. Right, and away you go. Right, it's the exact same thing every time. Right, so I've now got 1, 2, 3, 4 different print functions. They all print something different. Right. Okay, so what am I going to do? I'm going to make my variable. That's a pointer to a function, right? What kind of function does it point at? Points at any function that returns void, takes in one of these. Right. What can I do with my pointer? Right. I can make my pointer point at print int. Right. I can now print out the int x by dereferencing the pointer, passing in the address of x. Right. Then print a new line. Now I've got a double. I can take my pointer and now point it at a different function. Right. How do I print the double? Dereference the pointer, pass in a pointer to a double value, and away you go. I can take my pointer, make it point at a function that can print a string. Right. I can then use the pointer to call the function and print the string. Does it work? Hopefully it does. Of course it doesn't. Oh yeah, I don't know what point2 is. Sorry, because I don't have the structure defined here. So let me comment that out. But it would work if the structure was defined here. And voila, right? 1 minus 99 is just 220. Works just fine. Right. Again, you don't have to take the address of here. Right. It's a pointer to a function, so you can just specify the function name. Right. Again, because it's a pointer to a function, you don't have to dereference the pointer. Right. You can just use the pointer name itself. And everything works just fine. Right. Okay, so how are we going to use this in our program? So inside of the stack implementation itself, we're going to ask the user, hey, please give me a function that can print out an element of your type, right? Because you as the user, you know what the element type is, right? As the stack, we have no idea what the element type is. So what does this look like in practice? Right, so in practice, what ends up happening is the following in the header file, right? This is where typedef becomes especially useful, right? So because we know that our print function is going to need a pointer to a function, right? It's nice to make a typedef so that the user doesn't have to type in something gross that looks like this, right? So to make a typedef, we can do the following. Right? So here's the word typedef. I'm just going to declare what looks like a pointer to a function variable. But instead of being a variable, now it's the new name or the alias for the pointer type. Right? So pointer to void, sorry, returns a void, takes in one of those as its argument. Right? And now the name qlgstack underscore print underscore func is an alias for a pointer to a function that returns one of these and takes in one of these. Right? And so now I can use this name as an argument for one of my, as the parameter type in one of my functions. Right? So in the print function, there it is right there. Right? So in the print function, it asks for a pointer to a function that can print one of the element types. Right? Everybody got that? Any questions? So how are we going to use this inside of our function? Well, now it's easy, right? Instead of calling printf, instead of calling printf to print out the element, we use the pointer to a function to print out the element, right? So use the pointer to print out the element, right? And that solves the problem of we don't know what your element type is, so I don't know how to print it, right? The solution is ask the user for a function that knows how to print the element, use that function, print the element each time, right? And away you go. The exact same thing happens in free, right? So in free, we now have a second issue when we free the nodes in this, when we free our nodes in the stack, right? So where's pop? Pop has the same. Hopefully, I did the same. Oh, right. Okay, so we'll come back to pop in a second. All right. So in free, we possibly run into the same issue, right? So remember in our previous version of pre, we have to release the memory that's allocated to each node, right? So there's where we free the node. Right. In this situation now, though, our elements are all being held by pointer. Right? And it could be the case that the user doesn't want to free the elements themselves, right? Presumably, they were the ones that created the elements at some point, right? Then they passed in pointers to those elements, right? When they get rid of the stack, they may want us to get rid of the elements as well. The problem is we don't know how they allocated those elements, right? Maybe they used malloc. Maybe they did something much more complicated. We don't know, right? So we can't simply free the elements, right? We might have to call some function that frees the element instead, right? But we don't know what function to call. Who knows what function to call? Well, the user knows what function to call, right? So just like in print, we can ask them to provide a pointer to a function that knows how to free their element type. Right? So now we have a second pointer to function type, which is declared also in the header file. Right? So in the header file, we have a type def, right? So QLG stack free func, right, is just a name for a pointer to a function that returns void and takes in a pointer to void as an element. Right? This can't be const here, right? You're going to free the element, so you can't. This can't be marked const, right? You have to actually destroy the element, which means you need to write into it. So this can't be const, right? So the user is going to pass in some function or a pointer to some function that can free one of their elements. Right? While you're iterating over the nodes of the stack, right? Before you free the node, you're going to check, right? Did the user actually pass in a pointer to that function? If they did, they want us to free the element. So free the element by using their pointer to call the function that frees the element, passing in the element to be freed. Right? If they pass in null here, that means they don't want us to free the elements, right? They're going to do it themselves, right? And so it's the if statement, the body of the if statement doesn't run if pointer is null, right? Instead, we're just going to free the node, right? Whatever element was being pointed at in the node still exists after freeing the stack. Right? And so that is how you make a pointer to a function and how you use a pointer to a function inside a data structure like QL stack. Anything that's generic is going to anything that you make that is that has a generic type and relies on the actual type of the element being pointed at needs some kind of function to work, needs a pointer to some kind of function to actually manipulate that element, right? Our stack can't actually do it. It doesn't know what the element type is, so it needs extra information to process the elements. And so the rest of this notebook just goes through what I just talked about here, right? So if you had trouble or following that discussion, the notebook goes through great gory detail, exactly everything that I just talked about. Right, so you can read that to refresh your memory or to hopefully clarify anything that was confusing after the lecture. Does anybody have any questions about what just happened? Is a little bit, the pointer to a function syntax is weird, right? It takes some effort to get used to, but it is strange. Once you get used to the fact that, once you get used to the syntax, using it's relatively straightforward, right? You just treat the pointer name as though it were the name of the function, and away you go. There's another demo program here that you can run as well. I think it's the same demo program as before, but this one takes in a generic. What does this actually do? Oh, so this is all int as well. Is there a warning here? Okay, there's a few warnings that you need to be aware of when you're using this particular stack. Where's the demo program? Sorry. I just want to see how I did this because I bet, okay, this is good. All right, so remember that when you're using this particular kind of stack, your elements are being pointed at by a pointer, right? That means whatever is being pointed at probably needs to be dynamically allocated, right? So if you use QLG stack and you want a stack of ints, right? You can't just make a bunch of little local int variables and pass in the address of those int variables when you push them onto the stack. Right? The reason you can't do that is because those int variables only exist for the lifetime of the function, right? If your stack persists over more than just that one function, then when you exit that function, those int values no longer exist. So the pointers that are inside the nodes belonging to your stack are now no longer valid pointers, right? And when you go to use them afterwards, it blows up on you. So in the demo program is very careful to dynamically allocate the values that are being pushed onto the stack, right? So if you compare this to the previous example here, there'd just be a regular old int. But now this demo program dynamically allocates memory for an int, right? And it pushes val1 onto the stack, right? Similarly here, it pushes val2 onto the stack, right there. Right? So you have to be very careful when you use this particular kind of data structure, right? The elements are being held by pointer. Whatever is being pointed at has to last at least as long as the data structure itself. Right? If they don't, then at some point when you go to use your data structure, the elements that are in the data structure are no longer valid. So be very careful when you use this particular type of data structure.